Alright, so 7.9. Suppose that the fallout from a nuclear weapon is approximated as an infinite plane source of 1 MeV photons at the Earth atmosphere interface. Air density is 1.225 gram per centimeter cubed. Is that right?
Milligram.
Okay, so that's really heavy. That's like water. So aerial survey reveals that the exposure rate is 1 MR per hour at an altitude of 1 kilometer above the interface. Estimate the exposure rate 1 meter above the interface, accounting for buildup of scattered gamma rays. So we're going to model this as an infinite source. This just goes forever in all directions. And you're up here and you're observing this. Well, infinite square is the same as an infinite disk, so we're going to view this as a disk, as infinite. So we're going to use equation 720, which talks about the disk source in an infinite attenuating medium whenever we do account for buildup factor. So I'll write that equation here. So some dose is equal to that response function for that dose, the area source of the ground, over 2 times E1, which is the exponent integral function, and that's what it's called. It's just an ugly integral that showed you till it can solve for you. Where this value right here, it's not a straight line, I'm sorry. But this value is theta naught. So you can use this equation for a disk source, even if it's not infinite. But since it's an infinite source, theta naught becomes 90 degrees.
That's why.
And if you so secant of 90 degrees equals infinity, and right, yes. So that pushes E1 to infinity, or E1 of infinity, which is 0. And this value, e to the negative 1 minus b mu h secant theta naught becomes e to the negative infinity, which is 1 over e to the infinity, which is 0. So this goes away, this goes away. So we're looking for, what are we looking for? What type of exposure? Oh, exposure. Exposure rate is equal to response function of exposure, area source, over 2, E1 mu h plus a 1 minus b times e to the negative 1 minus b mu h. And what is SA? Don't know, so we can find out. So you get some constants for these. You find A, you find B. It's air, it's 1 MeV photons. I didn't write that. 1 MeV photons. You find A, you find B, you find U, find R, all these values. So the first case is where X is equal to 1 MR per hour, where H is equal to 1,000 meters or 100,000 centimeters. And you're going to get this value in terms of centimeters, so you want to use that. So you break that down, you find your area source is equal to 1.2, about 1.2 times 10 to the 6 per centimeter squared per second. Is that about what you got? Yes. Okay. So now we can use this to calculate x whenever h is some other value. So now x is equal to response x SA 2 E1 mu at 100 centimeters minus plus A1 minus B E minus 1 minus e to the negative 1 minus B mu 100 centimeters. And you put your values. You get 1.8 times 10 to the negative 3 R per second. And that's what I left my answer as, and that's wrong because they want MR per hour. So what is that value in MR per hour?
6468.
Just 1 MR per hour.
6468 millirem hour minus 1.
It's milliranks. That's right. I was just clarifying.
Miller what?
Rankins, isn't it?
Rankins degree, isn't it? Like temperature?
So this answer 1.8 10 to the
What?
power negative 3 rem per second, right? This is right answer?
Yeah. Yeah. Matt, is that what you got?
Rankin?
Yeah.
Yeah.
What is that? You said Rankin.
Rem.
Which is a temperature.
What did I, what?
You said Rankin. That's Fahrenheit.
Yeah, Rankin.
Absolutely.
How did we solve
It
for
doesn't-
SA again?
Rankin
I'm
and
sorry.
Rankin.
SA?
Yeah.
We had this
German guy.
equation,
Yeah.
You know what I meant.
which we
This
said
isn't right.
x is equal to 1 MR per hour at a height
No,
of
it's not
100,000
really
centimeters.
temperature.
They gave that in the problem statement.
But you know what I meant.
Yeah.
So we plug in
You're
that
clarifying
value,
it's not
so we know this,
It's not
this, you
right.
plug into this, shield
Yeah.
detail, know these, know these.
You
Solve
find B and
for-
all the other stuff from shield detail as well.
What?
You find B and A from shield detail as well.
Do you?
Yeah.
I don't think so.
But
Yeah, you have to look it up. It's on table E6.
They're on the
E6.
page that has the tab for Berger approximation, which you should all have a tab in your book for the
Is it
Berger
really?
approximation.
What page is that?
Where is that? Because I've been looking.
220. I lied, not 220.
It says table E6.
222. What?
No, that's
Yeah, there's.
That's for the
nothing
Taylor
like
No, that's
on
definitely
page
not right.
220 or 221.
E6.
Which A and
Which page?
Table
I lied
E6.
to you guys.
It's in the back.
E6?
Appendix E. For the values for A and B.
Yeah, so this.
Yeah,
over
A and B
here-
is an E6. I lied.
Yeah, that's for calculating SA.
You can also get
and
from the
SA.
shield detail.
We calculated it.
The-
What?
I don't know if it's in there.
Yeah, it's.
Is it?
It is in there, yeah.
You can get it from the shield detail.
For this problem?
Yeah, that's where I got it from.
What B value did you get?
No,
Yeah, and
A
B.
and B in there. That's
Oh.
what
Oh,
that is.
should you still tell you those values?
Yeah.
Okay.
Cool. I didn't know if it was in there or not.
For this problem, if you were calculating the Berger approximation, for this problem, B is a function of E mu R, where R would be the distance between the point and the ground at a certain thing. For this problem, if it was a finite disk, and you weren't using this equation, if it was a finite disk, and you use this, R would be changing, you'd have to integrate. Does that make sense?
Okay.
But you can find the parameters A and B. A and B are not a function of R, not a function of R.
Yeah.
Okay?
Okay, and then my only other thing is how did we solve for E1 that second time, like at the different height?
Should you tell?
The shield detail? Okay.
Yeah.
Is E1 the integral of like
Yeah, it's a special integral. Yeah, it's in the back.
Seconds per hour. Seconds per hour.
Yeah.
Value inside that.
That is, so E1 is,
So there's 3 decimal points and then they'll get you.
Yeah, and then you just multiply by H, but 1,000
Oh my god.
It's page 489.
1.8?
is that? So yeah,
I kinda went a little bit too crazy.
I think it's like,
Shield utility will do like a numerical approximation for it.
I think a lot of shield utilities just tabulated
Are you
values.
sure that-
Rates.
That,
That what?
hmm.
Did you get a different answer for the thing?
Oh, no, I'm just trying, no, that's right.
Yeah.
Okay.
like E1 to the, yeah, the second one, minus E1 secant theta, that's,
This?
yeah, the inside of it is gonna be infinity. Now, I got from shield details and just plugged in a very big number, and it just approximates to 0. Now, is that
Yeah,
how
because
how
that
I'm supposed to
exposure rate
think of
has
it?
D to
Yeah.
the side.
Well, this
So
is,
then
this
it
is
needs
that
to be
equation,
720.
e to the x is equal to,
D is no, is.
Right.
that's what that equation is.
No.
So if you plug in infinity here,
It just
E1
goes- your
of infinity
exposure
is
at
equal
the
to
1000 level, so
infinity
that's
to
your D,
infinity
you know,
of dt
well, D
e to
dot
the
R.
negative t over t. It doesn't matter what's happening in the integral,
Yeah, 'cause you know,
because
R,
these are the
D1,
same values.
and
So
then
you're
A,
integrating,
D.
it's just gonna be 0. It doesn't matter what this graph is, if this is x and y, if you're integrating from one to one, the area under the curve is 0. But yes, you could just put a gigantic value in the shield utility.
Unless you're in reactor theory, and then it's like not quite zero.
Yeah. Alright, good.